Okay, today we're going to talk about Group 11, Chapter 11, Group 2 Theory. Okay, let's go on. Now, um, the few things we need to talk about Group 2 elements is we need to look at again similar, the physical properties right here and the chemical properties right here. Okay, now so we're going to talk about the reactions with oxygen, water, and dilute acids. And then we're going to look at the behavior of oxides, hydroxides, and carbonates with water and dilute acids. Then we're going to look at the solubilities of hydroxide and sulfates, and then we're going to look at some uses of them. So relatively straightforward. At the end of the day, it will just be two things, like periodicity. Um, uh, Physical properties, chemical reactions. That's it. So for the physical properties, let us look at um, atomic radius, melting points, and first ionization energy. Now, atomic radius, as you go down the group, it increases. Why? Because as you go down the group, the outermost electron will always be one shell extra. As you go down the group, one shell more. Second shell, third shell, fourth shell, fifth shell. Because of that, the atom is only going to get bigger and bigger. Second, the melting point of group 2 elements. In general, the trend is that it decreases. Okay. Reason why it decreases, actually this one don't have to know. It is because group 2 elements, they are all metals, so therefore metallic bonding. But what happens as you go down the group is that the charge remains the same. The number of delocalized electrons remain the same because all donate 2 electrons. But the size of the ions become bigger and bigger. Therefore, what happens is that the forces of attraction between the sea of delocalized electrons and the positively charged ions become weaker. Why? Because now the ions become bigger. So the distance between the electrons and the ions, okay, increases, therefore become weaker. Now you may ask, there is a certain anomaly here where this one drastically increase, like right here. Don't worry about magnesium. This is what we call an anomaly. So the biggest idea why melting points of group 2 elements decreases, if you want to know the reason, it is because the metallic bonding becomes weaker and weaker. And the reason it becomes weaker and weaker, the charge of the ion increases. Now, first ionization energy. Hold on. Okay. First ionization energy decreases, if you notice, down the group. Reason as to why. Okay. Because as you go down the group, the distance of the outermost electrons and the nucleus increases. Shielding effect increases. Although your nuclear charge increases, the other two factors outweighs it. Therefore, forces of attraction between the outermost electrons and the nucleus decreases. Therefore, first ionization energy decreases. And that is why group 2 metals are more reactive when you go down the group, because it takes less energy to remove the electrons. Easier for it to donate the electrons. Okay. And that is about it for the physical properties of group 2 elements. Now, let us look at the reactions of group 2. We are going to look at some of them. First one, we are going to compare group 2 elements, okay, with water, oxygen, and dilute acids. Then we're going to look at the reaction of group 2 oxides, group 2 hydroxides, group 2 carbonates. Okay, and we'll finish it off by looking at the solubility and thermal decomposition of group 2 carbonates and nitrates. Just like periodicity, a lot of memorization involved right here. But this is what we're going to do, look at. Okay, now for group 2 elements with oxygen, beryllium, the first member doesn't react with oxygen. The rest all react. By the way, don't just assume it's calcium. It can be magnesium, it can be barium, it can be strontium. Okay. As you go down the group, it becomes more reactive because it is easier to donate the electrons. First ionization energy decreases. So more reactive down the group. And you just need to remember, key point right here, they will always form oxide. React with oxygen, always form oxide. Calcium oxide, magnesium oxide, strontium oxide, barium oxide. Okay, more reactive down the group. Okay. Now, as for the reaction with water, beryllium doesn't react with water. The rest all react with water to give you hydroxide. Calcium, barium, strontium all react with water to give you hydroxides. Except for magnesium. Why? Okay, again, this is quite straightforward. But magnesium, please don't forget, magnesium got something unique. Magnesium got these two parts. Cold water, what do you form? Hot water, what do you form? So please remember, for hot water, it will form magnesium oxide. When cold water react very slowly to form magnesium hydroxide. Please refer to the periodicity, the chapter, for the reactions of magnesium with water. Okay, remember, magnesium got two types of reaction, either with cold water or hot water. But not necessarily will give you hydroxide. Okay. Now, with dilute acids, beryllium does react with dilute acid, so beryllium will react with all of it. Now, calcium, so you can replace the calcium with either magnesium, or you can replace it with either strontium or barium, but the end result is the same. Metals react with the acid to give you the salt and hydrogen gas. So the anion will be from whatever type of acid that you are using. Okay. Now, just to clarify, later we'll come back to this. Beryllium sulfate and magnesium sulfate are soluble in water. Calcium sulfate is sparingly soluble. Strontium sulfate and barium sulfate are insoluble in water. Okay, so for this part, group 2 elements, beryllium does react with dilute acid. This doesn't react with magnesium. This doesn't react with oxygen and water. Okay. Sorry. Now, let's talk about group 2 oxides. All your group 2 oxides will react with water to give you your hydroxides. All your group 2 oxides will react acid to give you salt and water. Relatively straightforward. By the way, I'm using calcium as a generic one. You can replace the calcium with other group 2 elements. Group 2 metals. Okay. For hydroxides, straightforward. Your hydroxides, just like your oxides, will react with the dilute acid to give you salt and water. So it will always be this standard lah. Okay. Now, in case you are ever um, like you feel there's a lot to memorize, right? You just need to remember this. Think in terms of general. Don't try to memorize like equation specific unless like it's very difficult. Generally, why I choose like a general calcium, it is because I want to showcase you must remember the general equation. Like your hydroxides react with acid, form what type of salt and what type of water. If you remember this part, then you can easily set up whatever chemical equation that you need to. Okay. Now, your group 2 carbonates is insoluble in water. Please remember that. Let me highlight this. Insoluble in water, because I think this came out once. Insoluble in water. But your group 2 carbonates is just like your oxides, will react with dilute acids. Just that, not salt and water. It is salt, carbon dioxide, and water. So the difference between this is there's the addition of carbon dioxide when you react with group 2 carbonates. Okay. Now, this is a very important thing to take note of. I want you to clarify between these two. If you are talking about hydroxides, right? Please notice hydroxides. It actually increases. The solubility of group 2 hydroxide increases going down the group. That means barium hydroxide is actually very soluble. Okay? So remember, group 2 hydroxide does dissolve in water, but it depends. Magnesium hydroxide does dissolve in water, but very sparingly. That means you still see the solid appear right there. But the solubility increases going down the group, meaning that once you reach until barium, right, barium hydroxide easily dissolve in water. So what that causes, when it becomes easily dissolved in water, your solution is going to become more and more alkaline. Okay. Unfortunately, the opposite is true for sulfates. Your CaSO4, your MgSO4, it actually decreases. It actually decreases going down the group. Now, what does this mean? Is actually as you go down the group, right? Your sulfate, right, becomes less and less soluble. That means magnesium sulfate, when the highest near to the top there, easily soluble in water. Magnesium sulfate. When it becomes barium sulfate, it becomes less soluble, decreases down the road. In fact, barium sulfate, insoluble already. So I want to highlight between these two because it's something you have to remember for your AS. As to why the two trends is opposite of each other, you need to wait until A2. Because the answer is in lattice energy, that particular chapter. It has to do with energetics. But for now, please remember the solubility of group 2 hydroxides increases going down the group. The solubility of group 2 sulfates decreases going down the group. Now, thermal decomposition of group 2 compounds. For group 2 carbonates, please remember, this one I want to highlight a bit more because this one is come out quite often. Now, and a lot of people have some confusion about it. Let us talk about carbonates first. This one's straightforward. You have learned it before. Heat up calcium carbonate, you're going to get calcium oxide and CO2. You have done this experiment before, it will turn your lime water milky, the CO2. Nitrate is of a different ball game. When you heat it up, it is the one time that when you heat up, you will first release normal gas, then you will release what we call NO2. Okay, gas. So that one will be what we call a brown gas. Because of that, this is an endothermic reaction. Okay. both of this is endothermic reaction because you need heat in order for the decomposition to happen, both of them. But group 2 carbonates, again, let me reiterate, it's just a salt and carbon dioxide. Group 2 nitrates is a salt oxide, nitrogen dioxide, and oxygen. Please, yeah. And this nitrogen dioxide will be a brown gas. Okay. Now, because it is an endothermic reaction, now the temperature of the thermal decomposition, highlight please, increases going down the group. Meaning that as you go down the group, the temperature needed for it to decompose for both carbonates and nitrates becomes higher and higher. Let me state this again. For carbonates and nitrates, the thermal decomposition, the temperature needed for it to decompose becomes higher and higher going down the group. If let's say magnesium carbonate need maybe 100 degrees Celsius or 200 degrees Celsius, barium carbonate will need maybe 400 or 500 degrees Celsius, definitely higher. The reason behind this again lies in A2 chapter, lattice energy. But for now, AS, you don't have to know the reasoning behind it. For A2, you have to know the reasoning behind it. Okay? But please remember, this type of questions regarding thermal decomposition is a popular question in paper 1 and paper 2. Okay. Unfortunately, pure memorization time. Please remember, brick red color, strontium when it burns. So that means, what does this testing mean? It means ion flame test. When you burn the compound, anything that contains calcium ion, strontium ion, or barium ion. For calcium, it will be brick red. For strontium, it will be scarlet red. For barium, it will be green color or apple green color. So these are the way we test if the compound has any of the ions present. We often burn them. This is what we call a flame ion test. And the characteristic color will tell us what type of ions is inside there. Yeah, that's all I can say. You do not know why, you don't have to explain like why it would come with that color, but you have to remember what color is associated to what ions. Yes. So when the question asks that the compound burns with a brick red color, that's your indicator that the compound contains calcium 2+. You have to remember this three. Last but not least, we come into the uses of group 2. So we are done with the reactions of group 2 compounds already. Is that all the reactions you need to know? The answer is yes. Now, for the uses of group 2, there are two types. The main major one is magnesium oxide. Magnesium oxide or magnesium hydroxide used to neutralize excess acid in stomach. One of the compounds, if let's say for the medicine for gastric, when too much acid at time. Or magnesium oxide used as like in periodicity, refractory linings in kilns and furnaces, because it is one of the main components of ceramics. For calcium compounds, the main one is limestone, calcium carbonate. Often can use the marble for tiles or use it to make buildings. You can make cement by heating up calcium carbonate. It will decompose to form calcium oxide. It's what we call lime or quicklime. Then your lime and quicklime you can mix with clay to make cement. Then your cement mixed with sand and rocks to make concrete. So one of the main components of concrete is calcium oxide. Okay. Another way that we often use is to use this limestone, add water, we form what we call slaked lime, calcium hydroxide. So this is called slaked lime. If we dissolve calcium hydroxide, you know what we get? In water, we get calcium hydroxide equals lime water. So lime water is actually calcium hydroxide aqueous. Okay. So these are among the few main things we use limestone, lime, slaked lime, lime water, things like that. Okay. But these are the major uses. primarily it's for magnesium and calcium are the one that's majorly used in the industry, uses of group 2 compounds. Okay. Okay. But the most important I would say is that for group 2, right, is actually the physical properties is easy to understand, but the highlight of this is right here. You have to know every single reaction of them, what they form, give the product, write a full balance equation. There is no escaping of it. Thermal decomposition, the solubility decreases or increases, all that must know. So the most important component for this particular chapter is reactions of group 2. With that being said, thank you very much.